Welcome back. It is good to see all of you here today. I know we were hoping today would be our demo day for MP4, but I think it's good to wait a couple days and put a pause on that. Have one more lab time to do some debugging together and to discuss some things. Part of the reason I also wanted to delay is when I look at this topic that we haven't really gotten through, which is just looking at lighting and some of texture mapping. It's been a little unfortunate. I think we've been really getting to the point of getting very basic shading done in the lab that we've been really happy when we've gotten, a red triangle and a moving triangle. But the truth is, once you have that working, there's so many other really cool things you could start to become, creative with and really be able to demo. And it would be great, even if you feel like you've done enough in MP4 and you're pretty satisfied with what you've accomplished, if you can take the next couple of days and say, well, I have this working platform. Let's think about what will actually work. What kind of shaders can I write that will actually work with our compilation and execution infrastructure we have to be able to demo some reasonable things, and what is the resulting performance of that? I believe none of you have texture mapping working, and we will talk about that in practice. The main thing I believe that is missing right now is the compiler emitting a single instruction called texture or texture lookup. As we will get to, hopefully, if I get started, as we will get to today, that actual operator or instruction is relatively straightforward. That thing itself is not doing all that much. That sampler uniform that you see in those shader examples that use texture mapping and the actual texture lookup itself is a very straightforward instruction. What is not straightforward with texture mapping, and we're seeing this a little bit also just with regards to depth testing and alpha blending, what is not straightforward with texture mapping is the almost exponential configuration space for what you can do with your texture fetch units. And I think that's part of the challenge. That's the same challenge you are all facing for your project, but that's definitely a challenge, which is we know that we can't implement all of it. We just can't. What is a reasonable subset of credible functionality for texture mapping? And I'll give you some suggestions today. And I think with those, you should also still be able to get that to work, because it is really just one way to think about it would be one somewhat configurable instruction that you're just doing no different than a load instruction that we're already supporting, but more maybe a two-dimensional load instruction is what we are doing. But otherwise, I'd really like the teams to get and feel good about what they've accomplished for MP4. And so maybe 2 more days will suffice for that. So definitely you should be able to show depth. A lot of teams have, and alpha blending, and a lot of teams have done that as well. And then look into any of the challenges associated with just adding a second shader module with regards to meeting timing or fitting the design on the chip, and showing that you can run programmable code both in the vertex and in the fragment shader. Because I think if you get the pass-through working, which a lot of teams kind of stopped with for MP3, if you get pass-through working as well as that simple scaling one where it kind of moves the triangle around, that means you have loads and stores and additions and multiplications working. You can do a lot of fun things with that. Even if you have none of the special function units working, you're really just limited by, I would say, your creativity and thinking about what would make a good programmable shader. So that's the reason I also wanted to continue on this topic today, which I think may seem a little dry, but I actually just want to give you a little bit of motivation, perhaps, to kind of dig into the shading side of things and play around with what you can do just in OpenGL on your own workstation or on the remote workstations, and also what subset of that functionality should still be something you could get to work using your SGP hardware. Because I do think, and I understand, we're always just trying to kind of get to the deadline and get something that's reasonable and be done with it. And maybe with a couple extra days, you can also think about what would be a cool demo, what would be a cool way to show off our capability. Because right now, well, we haven't done that, I would say, for shading. I think that's a fair statement so far, that we have programmable shaders, we have all this compiler infrastructure, you've built really cool looking little multi-cycle processors, and we don't really use them for anything. And that seems like a shame. So it'd be nice if we could start to demo some of that functionality. So this is about a week ago now, where I left off when we were talking about the different aspects of the Fung shading model. And this is the specular aspect. We were talking about there's really a coefficient, which is how shiny should the object be. And there's different ways one could implement it, but with the cosine of phi to the alpha term, That's looking at the angle between the normal of our shape and the surface normal and the light direction. And based on that, that alpha term is basically an exponential term that says how quickly should that lighting highlight kind of tail off over time, over space, I guess, as you get further and further away from a direct uh, perpendicular intersection between the light direction. So you can get different type of material properties just by changing that property. Nothing else is different between these nine rendered spheres here. Only difference is that alpha parameter is being changed. And I know we had talked about, and I could briefly bring it up just to make sure we're all still on the page here. We were talking about the three components, and the first one was the diffuse component of our Phong shading model, which is just general brightness of the object based on that interaction between the normal and the um, and the light point source from direction, such that if it is perpendicular, you get sort of a full reflection. Otherwise, you get some the varying amount based on the angle between the light and the normal, and if it's completely uh, flat to it, then if the angle equals zero, then you get no light reflected back out. So that's the diffuse component of the model. Then there's the specular component, which was this term, and it is using a cosine term then raised to that exponent to give you that type of highlight. And then finally the final term. So there's these three different components of it. The final term is the ambient term for this. So none of these individually, and this is true of the entire Phong models, but none of these individual terms necessarily can truly be justified from like a physically based rendering perspective. This is trying to reason about how we can simulate light in a scene. And while we have these point sources, well, real lights aren't actual point sources. We're not shining laser beams into a scene generally. We have lights, and they are lighting a scene generally. And so this term is a little bit of a catch-all, which is even if there isn't a great interaction between the direction of the light and the surface normal of our object, that doesn't mean it should be completely black, right? There's still generally, if there's a light on in a scene that we want to render here, we would have some background light, and that's what the ambient light is. And that's just kind of a catch-all term, which is no matter what else we have in terms of the diffuse response or the specular highlights in our term, we have a little bit of background, this ambient light, and we have a separate term associated with that. Um, and this point with regards to the distance term isn't super relevant anymore. But I think what is relevant is now we have those three components of light, and each of those components themselves have separate RGB aspects of them. So when we think about the terms we would generally need to specify for the Phong shading model, there's actually quite a bit. So for each light that we want to have in a scene, we would want to think of how much of it does it contribute to the ambient lighting, the diffuse lighting, and any specular lighting for the objects that are in our scene. And for each of those three things, then it's the R, G, and B. So you can imagine we think of light as being white, but it's not necessarily so, right? We could have a red light and a blue light, or any colored light we may need to have in a scene. And that's for every particular light source. Again, from a physically based rendering perspective, there's no actual justification for that. What does it mean to have a light that provides blue ambient lighting, but red specular highlights and green diffuse, responses? It's at least it's hard to reason about that from a physical lighting perspective based on what we know about how light generally works. But it's a good hack to get a reasonably accurate looking scene back out from that. So for every light source, then we have those nine parameters. And then for every object we have in our scene, we also would have nine parameters because it's the reaction between the two. It's the intensity of the light as contributing to the diffuse in the RGB, the specular in the RGB, and the ambient in the RGB, and it's to what extent the material of that object reflects or absorbs the light in that same amount of component. So there's actually then for each light source we would have nine terms, and also um, for each of the objects or just material types in a scene, we would also have nine of those coefficients. So there is generally a lot to keep track of. I mean, again, for often common cases of lighting and showing a scene that has lighting in it, you're not thinking of the entire design space of all those parameters. But the math works out being the same. And then there is that 10th parameter there, that shininess coefficient. So how shiny the material is, how much of a highlight does it show, or how much of uh, uh, a more diffused highlight is it showing there. But that is a lot of things to keep track of, at least in theory, that for every object, you could have those 10 coefficients. And for every light source, you could have those 9 coefficients. The math works out to be the same. That's a good point, Matt. The math works out to be the same, right? We have those 3 components of the Fung shading model, and whatever we provide, and we would provide those as uniforms in our code, right? Here are the light sources, here are the material properties. Whatever we provide for those, the math works out to be the same. Given our properties of the object, both material properties and relative position and surface normals for those objects, and the location and the properties of the lights, we run the same math. And so the shaders wind up looking relatively straightforward, and it allows us to model essentially all the basic kind of things we want for three-dimensional looking objects um, using this Fong shading model. And if you want to look at kind of the mathematical breakdown of what our Fong shading model then is, it's that. That's for every light source and for every component of the light source and interacting with every object in our scene, we would be calculating this term here. The light, the color, the shade of that particular vertex or fragment without actually writing the distance terms would correspond to this. So we could start from right to left here, right? We have given material properties of an object and light properties, we have some ambient term that we're calculating. You can think of that as like the background light, right? The constant offset of our light. Then based on how the light source and its properties is interacting with the viewer and the reflection of that light source, you can't see my hands necessarily, the viewer and the light source, that's our specular highlight, and that's this term here. How much of a highlight it is also specified by that 10th term here. And then there's the diffuse response there. So based on our light and the surface normal of the object, there is our diffuse background lighting for the object as well. So we do that for all of the color components, and we add all of the contributions for all the sources. And that's what we would do in our shader. And that is the Phong lighting model as applied in our shader. There's still a little bit of thought required in terms of which shader we choose to do that in, because you can choose to do it either per vertex or you could do it per fragment. Both approaches are valid. There's just different trade-offs of performance and sort of smoothness of the resulting scene that we have out here. I'll show you a couple demos of that in just a moment here. It is technically the case, and I don't think it matters so much from our perspective, in which we would probably just be following a recipe for applying a Fung shading model, that this, while it's very similar to this view angle dot product with the reflection angle, is slightly problematic because it is calculating a new thing per vertex, whereas we already would have this information stored as an input to it. So when we talk about the Fung shading model, what is still most common is instead there's a calculation of a halfway vector. This is the Blinn modification of the Fung shading model. I don't think the detail matters so much, but it turns out that in practice, that instead of calculating v.r, instead we calculate n.h, and that allows us to do a little bit less math per vertex, with the result that looks roughly the same. And I wouldn't worry too much about that, but that is if you see descriptions or documentation referring to the Blinn Fong lighting model, which used to be the OpenGL standard. The fixed function hardware was literally implementing this math for every incoming vertex and light source we would have. That's what that's referring to. It's the same concept. It just turns out that instead of calculating this, which requires quite a bit more additional math, you're given these normals as input, and calculating n.h is a little bit easier. You can get a very similar kind of result. But in practice, what happens is, yes, we're technically calculating then n.h with a new shininess coefficient versus, in theory, what makes sense, which is v.r, at least, which has a little bit more physical justification to it, raised to the alpha exponent. You get a very similar result, or you can get a very similar result by just modifying what terms you're using for those things. And at least in my experience, that when playing with the Blinn Fong or Fong shading models, there's a lot of trial and error involved in terms of, or alternately, it's starting with a set of coefficients that make a lot of sense, and then just adapting them, for your needs, because that is a very large parameter space, no matter what, right? In theory, for every light source, and we generally would not want just one, we would want in a scene all sorts of different light sources. There is a lot of parameters we could then specify, and the resulting things, frankly, if you're not careful, are going to look very white. That happens a lot. I have 5 light sources in a scene, and generally we add the contributions to all those light sources. And if you're not careful, everything is just blindingly white. That'll happen to you once as you're playing with different light sources. Um, Alternately, you get things that just look very unnatural, at least by default. So that's a very common issue to have as well as you play with these models, and just try it on your own hardware. Because as I mentioned, we should be able to support some version of this now by the end of MP4. It's not clear to me why we can't. So you get to convince me that that's not the case. But things like this, where the Utah teapot model, which you can find the vertices for it, or there's helper functions that just provide it as a buffer. Um, we should be able to get something like this with just modifying the parameters in that Phong model, or the blend Phong model there. Because now that we would have depth, that would be the final thing that was really preventing us from doing anything fun in 3D. And I think most teams do have depth working. Um, Switching over to the chat briefly. So, how do we present non-point lights? There used to be, as sort of a first class citizen in OpenGL, ways of specifying non-point lights. Um, the nice thing is this is our model for point lights in OpenGL. If you want non-point lights, there's really nothing stopping you from either modeling them as multiple point lights. I mean, that'd be one way of doing it, or doing a little bit more of that light interaction in your shaders themselves. So this is one such approach that, at least given early hardware limitations when it was invented, and the flexibility of it to allow for a lot of different lighting scenarios, is still in very common usage. With programmable shaders, within reason, there's all sorts of things one can model in terms of your light material interaction. So, if you wanted to model a spotlight, there's ways you could do that, right? You can model a spotlight as, 3 or 9 different point lights at different intensities. And it's really just an accumulation of those light values that you would get back. Um, Oftentimes, I mean, it depends on the needs, if this is a real time render or an offline render. Oftentimes, we don't use this lighting model at all when we're wanting to model lighting, and we pre-bake all the lighting, and we say, well, I want this really crazy kind of lighting effect in my scene, but it's going to be static, or static over a reasonable period of time. I will generate it offline and apply it as a texture map instead to my scene. Because ultimately, when we're talking about lighting, right? Let's go back to our happy fun ball example when we were starting this. How do we get things to look realistic, right? How do we get things to look maybe more three-dimensional, but certainly more realistic as well? And light is the reason why we can see things in the first place. But that's the ultimate goal of all of our shaders and the entire pipeline, is just determining, for the fixed number of fragments and pixels we're going to be displaying on a screen, what should that color be? So ultimately, this is just one approach. So if we want to consider point sources in a scene, and the different contributions of a point source to the color of an object in our scene, the Phong model makes a lot of sense, at least in terms of, it's popular, it's well studied, it's well understood. Hardware evolved to efficiently be able to support it, so it still makes a lot of sense for doing, and even in modern hardware. But ultimately, we have these programmable processors that take attribute data for our incoming vertices and produce pixels at the end. And the sky's the limit from that perspective as well. It's just the trade-off of how much time it takes to execute, versus the fidelity of the resulting render that you get back out. I don't know if that answered the question, but the true answer to the question is, well, it depends. There's a lot of ways one could do it. Um, Oftentimes, I do tend to see that either some relatively straightforward extension of a Phong shading model, or what we want to do is well beyond what's even possible. We just do it at least partially offline, and then ultimately these are just textures that we're mapping to our objects. Because you could do that, right? For what we have here, where these are in theory calculated in runtime, different parameters for the Phong shading model. These also could be texture maps, right? I know we haven't talked about it too much yet, but texture map allows us to just wrap the object and say, here's what the color of that particular location in the object is going to be. anything you can do with a runtime model is something you can also then do offline and apply as a texture map. So with that, the world is kind of completely open to your creativity to doing that kind of mapping. I kind of like this demo. It's old school OpenGL, but I don't care about it for the source of it, so we're not going to look at the source edit, but just kind of understanding how those parameters play together. So I'll show this to you briefly if I have the screen open here. Yep. Okay. The different parameters in the blend Phong shading model here. Can everyone see this? Okay. All right. Thanks. So here's our little 3D torus. We talk about the common objects we use for these. Some of these are going to be better than others for showing. We'll stick with the torus, I guess, to begin with here. And depending on how good this is showing up on your screen, you should start to see some of the things we're talking about here, right? Okay, we did it with the happy fun ball. You saw those teapot examples. Okay, here's another really basic three-dimensional object with a single light source. And that is what is determining what the color of this. There's no GL color call, or there's no color attributes being passed to a vertex shader for this example here. This torus is that color because we have a light. We have both a light and we have a material defined for the object, and they are interacting via the Phong model here. So why is this thing, I guess I would call it sort of a grayish blue? I think that'd be a valid way to describe what this color is currently. Well, first we look at where the light is. Okay, so there's our light position in space here, and you can actually show, this is why I like this, it shows where it is. And we can move it around. As we move it around, what should we see happening? Well, the position of the light relative to the object matters for two reasons, right? It matters for the diffuse component of the light model. So that gives us our general kind of shadowy kind of shade to it. And then it matters for any specular highlights in the model as well. That gives us our kind of bright highlights that are happening here. And it's the components of the lights themselves, as well as then what absorption properties that material has. So another way to answer that, why is this kind of a grayish blue here? And your answer is kind of found in the light itself is kind of boring. There's no ambient light here. So if we were to crank up the component of the ambient light, then this should become significantly redder as we do so, right? But with no ambient light as part of the component here, why is it kind of a grayish? And maybe it's not blue at all. Maybe it's mostly just gray, and I'm seeing it as kind of blue here. Well, look at our light model. A material properties of this object is kind of equally absorbs light at that equal ratio, and we know that when we have equal amounts of RGB, we get sort of a scale of gray, right? So that's why it's kind of gray. Why are we getting these particular highlights here and here? Well, that has to do with our specular model, right? With regards to the parameters that we have for the surface normals, which aren't shown here, but you can kind of imagine they could be calculated based on this being decomposed into triangles and where the light is coming from. I should be able to change the position of that light in XYZ, and then both the diffuse and the components and the specular components should then change accordingly. And change in a way, and the whole point of this again is that it's roughly realistic, right? We have the highlights there because the lights are coming from this direction. If I now change the direction here, let's see what would make the most sense to change. Let's move the light source in the positive direction here. This is dragging my mouse, which is very slow. And we've seen now the direction the shadows appear to be coming from are also, I mean, to the extent it's realistic, it does look like it's still a shadowed kind of lit object. And where the highlights are have also changed with regards to this object. Let's reset those parameters. Not going to play around with spotlights and things like that. That's not super relevant for modern OpenGL. But what we can certainly also then do is say, well, let's look at the different just pre-baked material properties here. So this was I'm not sure which one this is by default, but here's now a chrome model. Well, you get the same highlights here, but the actual color of it, the main difference is the light hasn't changed at all. What's changed is now the material properties, and at least for the diffuse properties of it, we're consistently gray. And for our specular highlights, there's a much higher exponential component there. So perhaps you could see when we compared the two that it's a lot more of a highlight, right? It's a more of a drastic highlight there. Looks much more metallic and much more shiny. We can play with any of number of these. Let's do. Black only goes so far here in terms of showing things. Black plastic. Okay, so we do black plastic. Here now, no diffuse or hardly any diffuse response at all. A specular highlight that's reasonably high, but is just also kind of medium gray there, and you get that kind of object. We'll go with ruby again. The only thing that's changing is I'm changing the different settings here. Is this matrix or these individual vectors corresponding to uh, ambient, diffuse, and specular? I think it would be nice to crank up the ambient lighting as well. That would give us probably a better feel for what the different color models would ultimately look like. And now you can see it, and that's the only difference. So the math that's being done is exactly the same. I think I've made that point well enough. And the math itself, although we kind of rushed through it a little bit, and there's dot products and cosines and exponents and things like that, it's not all that much. It is it is calculating our angle intersections here and multiplying it by these constant factors for R, G, and B, and then adding the result back. So in terms of what our vertex shader is going to look like, and let's open up a proper vertex shader here, it's also going to be a relatively straightforward thing. There's a couple caveats we have to watch out for, but it's generally going to be a relatively straightforward thing we would need to do for our actual vertex or fragment shaders here. Make sure you can see that. Okay, you can now see that again. Thanks. Um, so in terms of adding lighting to our vertex shader, there are a lot of those quantities in terms of the vector quantities we need to use for our lighting computation, and we can just walk through them, right? So now if we have our inputs and outputs of a vertex shader here, it's no different than what it was before. Um, it's very slightly different than what it was before. Um, in our vertex shader, we're still specifying what is the position, what is our XYZ for our incoming vertices. We are also now specifying, and I had already mentioned this, that we're specifying the normals for each of the vertices in our for our particular object in our particular scene. What I'd brought up, if you recall, I brought up the seal model and showed that generally, if you're dealing with a complex three-dimensional object, the normals would be provided as part of that object as the actual three-dimensional object specification. There's also ways one can calculate it using the cross product of the two vectors composing each triangle. Other objects like the sphere, the actual normal is something that could be analytically determined in a very straightforward way. So those normals would have to be provided. So you do have that responsibility now to calculate the surface normals for all the vertices in your scene. There's different ways one can do it, but generally, if you're grabbing a 3D model and trying to render it, those normals will have been done for you. You don't have to do it in your OpenGL code. And then our output is still the same. Our output is the color we are wanting to compute here. And there's now all these uniforms. We should be able to support all these for the most part in our GLSL compilation architecture and your shader cores that you've already built for the lab assignments. Um, Here, it's a little bit of a shortcut in that we could technically provide the ambient light source and ambient material property separately. So that would be the IA and KA terms in the model or in the previous example that I was showing. And that would have been equally valid. So that would have been two vectors for each one versus one. This is being called the product because in OpenGL, then that product, that multiplication has already been calculated offline or before entering the shader stage. That's fine. Either one would have been perfectly fine a way of doing it. What is also common, and I think the quick argument for this will probably suffice. What is also very common when doing lighting calculations in your shader is while previously when we were just interested in viewing and transformation of our vertices, we would be calculating a single MVP matrix, right? Model view, which is usually one matrix, and then projection matrix multiplied together to get that single model view projection matrix. that doesn't entirely make sense when thinking about lighting, right? So model view matrix, right? Our vertices come in and they get moved around. They get stretched, they get moved, they get put relative to our eye space, to our camera in our scene. And then projection is the matrix that dictates the capabilities of the camera. What kind of focal view does it have? How much perspective distortion is going to happen in the camera? What are we actually looking at? Or how are we doing the looking in our particular scene? And those are two different matrices, but because we can multiply them together and there's distributive properties that are okay, we were previously just providing that single matrix, that MVP matrix, as an input to our shaders. And what you'll see now for shaders that take lighting calculations into account, we tend to keep them separate. So, and to explain that so you can see it here first off that it's just two matrices versus one matrix that is being provided. Um, because that transformation that's happening with regards to each vertex, ultimately we're doing both transformations. We want to move it relative to the camera and we want to get it into the camera's view. But for the normals, we want to move them relative to where the object is getting moved. We're not actually viewing the normals, right? We're not actually doing that projection of the normals into anything. So we would typically not be actually multiplying the projection matrix by those normals. And likewise, while ultimately those vertices are going to be put into the projected view, and all the clipping and all that can be applied afterwards. When we're doing these lighting calculations, they're independent of the camera. So it doesn't at least make a physical sense to say that our light vectors are getting projected into a camera. So the light vectors are interfacing with our objects, and then ultimately it's our camera that's capturing that with whatever projection or whatever distortion we're having there. So we keep those separate, although we're still ultimately doing the same exact math on our incoming vertices. It's just done in two separate stages. So there's a model view transformation. If we're wanting to move our camera around, we still have to do that. If our camera is not looking anywhere near our object, that's relevant for our calculation of these light intersections. But then the actual projection happens as a separate step. So that's why you see those matrices happening as two separate calculations that are happening there. So in this case, then we have some intermediate variables that we require for our shader, which we haven't been dealing a lot with. But we would start with the model view transformation. That's transforming into camera coordinates or eye coordinates here. We're then doing the actual vector from the calculation of the vector from the vertex to the light. There's mathematical reasons these are all normalized. We're using these to calculate our dot products as a mathematical hack to figure out the angles between these intersections. So the dot product only is equal to our cosine if each of the vectors are unit normals. So there's these normalized operations that are happening here. We then would calculate the I vector. That's the vector from the vertex I space position to the origin. And then, although we went very quickly through it, for the Blin-Fong normalized model, modified model, we're doing the half vector. That's the normalized halfway between the light and the I vectors. There's also N, that would be the transform vertex normals. We don't need to use vec4s for any of these. There would be no harm if you did, but here we're dealing with vectors and not actual, homogeneous coordinates. So there's an operation that allows us to do it. But here's the actual lighting computation that's happening here. So in the Fung model, which is what this shader is based on, we're using all these material properties. So you're seeing that as part of the code here. Also, each light can separately contribute to those same properties. So that's the product variable that we already have in the shader here. So we transform our vertex normal. We then start with, well, here's the ambient component of the light. That's just given as a constant. We then do our dot product of the light vector and our surface normal to figure out how much of a diffuse component there would be. The fact that this is called KD is a little unfortunate because that was the same variable we used to define the material property. But either way, could have been called CD. This is the calculation of our dot product for the diffuse product. We then multiply that together. Like now we do the dot product of a normal and that halfway vector in the modified Blin-Fong model, and exponent raised to our shininess coefficient here to get our specular component here. If we wind up with a negative value, we want to correct for that. There are ways to do that. That's one way to do it with a branching statement. We do still finally do our MVP transform. That could have been done earlier. It didn't have to wait, but it has to be done at some point. Because we're still doing that forward transformation, that calculation here. Another way to think about this if statement is really if the light is behind the object, we want to make sure we're not contributing to the specular component there. That would happen. You'd get a negative dot product. And then finally, for our color computation, we're adding those three components together. It's the sum of the ambient, diffuse, and specular colors, and you have the updated transformation, and that's the output of our vertex shader. That would be per vertex lighting in our shader. Question about discard operation. Discard operation. That's relevant for our fragment shaders. We could support it. Right now, we would have to have. I mean, I think we could, right? So discard says that's one way of providing a type of control flow in our fragment shaders, which is fragment comes in, and for whatever reason, and there can be all sorts of reasons, don't even process that fragment. Drop that fragment entirely. Just thinking about how we implement things currently, we have our thinking a little bit off the cuff here. We have our shader core implementation, right? That detects opcodes and does processing, and ultimately we are spitting out something into the FIFO, right? So at the end of every shader, both vertex and fragment shader, we spit out something into our FIFO. So at first glance, your first thought, you think, well, we can't support discard because we're always spitting out a FIFO. So how do we discard something? But I think it's also possible, I mean, as a hack, if you get a discard operation, you could just set the value to all zeros or something, right? That'd be pretty close to discarding it, or setting it to an invalid coordinate, something that's guaranteed to not update the shader or update the actual color buffer. So one could come up with a way that would kind of hack and get you a solution for that if you really wanted to support that. So I think actually that, I mean, right now we don't emit an instruction, we don't have an opcode for that, but those are all very easy to solve problems. I think in 5 minutes you could look at that part of the compiler we provide and say, if the spear v opcode is discard, generate this instruction. Right now it'll just spit out an error, but that would be a very easy thing to add. If you really wanted it, you could certainly support that. That was kind of random, but that's fine. So anyway, this is our vertex shader for doing the modified Fong model, and I can just briefly show you, what that looks like in terms of code in practice. So here's a very basic light model code here. I like this one because it's all just self-contained in one file, and it's slightly different than the example that's we had on the slide, but it's doing very similar things. So we're going to have all those uniforms. So we need all those handles to the uniforms and finding them in our shaders themselves. We have the actual vertex shader here. This one is a little bit different than the previous example in that the vertex shader, if we take a look at this here, takes the model view matrix, takes the projection matrix, takes an input position and takes an input normal, and just does that transformation. So here we have our MVP transformation. And then we have our actual normal transformation, which we're only applying the model view matrix to it. We wouldn't want to apply a projection matrix to our normals, right? As our objects get stretched and distorted, that doesn't change the value of the normals themselves. That's just for the vertices that we would be doing that for. And then now actually here, the Fong model is being applied in the fragment shader with a couple of hard-coded hacks in there. So in this case, we don't have separate uniforms for all of the ambient product, diffuse product, and specular product. one could easily refactor this code to do that, right? To say, um, provide that as a separate uniform versus just having some hard coded value. Um, we have also a hard coded light position, but that also is something that's a little tricky when being done in fragment space, because now that's actually being applied in the sort of pixel space where our actual light position is here in our screen space. It's being provided at that point, but then the math is still effectively the same as what we had here before. I don't recall if I changed that or if that was already changed, but that had no specular highlight, so we can add that back into the code example here and just quickly run this, but I may have to recompile. Let's see what we have here. That does have the specular highlight. So that version did have it compiled in there. Um, Very similar to the previous example that we showed with it happening. The only difference now is it's rotating, so you can see how the light changes just by changing the model view coordinates of the individual objects here. And yes, these examples are always teapots or Tauruses, tori, I don't know. We always start with the basic things. When you're doing, for all of our rendering of rasterization approaches and transformations, we were sticking with triangles, right? Because triangles, we can understand what's happening. This only generally makes sense when looking at three-dimensional objects, so we're picking some of the simplest three-dimensional objects. Spheres aren't all that great either, because then you can't see things like multiple specular highlights for a single light source on a sphere. So you tend to see a torus model used for these examples. But let's talk about that difference between the two code examples, the one that was on the slide and um, the one that was in that OpenGL example demo code there. There are actually three different types of applications of the Phong shading model. So the three types you'll see is just Phong shading. You'll also hear the term Gerard shading and then flat shading. And these roughly would correspond to per vertex shading, per polygon shading, and per pixel shading. So that previous example, um, this code is technically per vertex shading. So technically, if you want to use the exact right term, I don't know how much we care about giving the right inventor the right credit for it. That's technically Gerard shading, what we were doing, which was per vertex shading. But there is a fundamental limitation of doing shading in the vertex shader, right? Polygons generally, our triangle tends to have just a single surface normal. Surfaces normals are only really mathematically defined relative to um, to to surfaces, right? Not to individual vertices. So generally, there's multiple ways we can approach that. So the per uh, polygon shading model or flat shading model is just to assume that for the three vertices that compose each triangle, assume that they all have the same exact normal. That is fine. There is some validity to that approach. That if that's all we have for each normal is for each vertex is a single normal value for all three in the same triangle, what you get is that um, per polygon shading, where because each of the three vertices in your triangle, if they have the same normal, their math in terms of calculating in the vertex shader the contributions of the specular and the diffuse terms of the shading model would be the same. And so we call it per polygon shading or flat shading. The reason for that is because it winds up looking pretty flat, right? If we only know the surface normal on a triangle by triangle basis or polygon by polygon basis, our shade is going to look like this, our resulting shaded model. And again, the reason for that is when we look at the math that's happening in our vertex shader, the interesting math that's happening right here in our vertex shader, this normal and its contribution to the various components here is going to be the same for all three vertices in each triangle. If that's the only information we have, if we have per triangle normal information and we don't do anything with it other than just apply it directly, that's why it's referred to as a flat shading model, because you can see the individual triangles still. It still has a three-dimensional look. The cow looks okay, the bull looks okay here. It's fine, but you can see the actual individual polygons. Um, For a distant viewer, or without worrying about any particular highlights, the shades for each individual triangle is going to look roughly the same. There's workarounds for that, even with flat shading, per polygon shading. If you have enough polygons, and this is both, this is the same model being applied to both here, it looks better, right? I mean, ultimately, as our triangles get smaller and smaller, no matter what kind of flat shading model we are applying, you get a reasonably good result. As our triangles get to the size of individual fragments, you get a per fragment model, not for free, but without having to worry about it on a fragment by fragment basis. So you're absolutely right, Matt. So that is a very common approach. If we want to do things, there's two approaches to consider here. That is the flat model, that is per polygon shading. We can also do per vertex shading if we have some sort of approach um, to calculating a different surface normal at each vertex. And when we refer to this Gerard shading, which is a very common thing we would want to implement here, we can actually do so via just a very simple kind of average and say, well, for my particular vertex, as I am determining the surface normal for it, I know that this vertex, if we're part of a mesh here, is connected to multiple polygons. You can think of it as being connected to multiple triangles, right? And so the Gerard shading the Gerard shading application of the Phong lighting model is to do that, is to find the average normal at each vertex, and then to still do sort of a per vertex shading. And then the interpolation that happens is still our traditional color rasterization. So it's not quite the same as this entirely flat thing where there's actually very little interpolation that's going to happen. Let's see, you can't see my mouse cursor. There's very little interpolation that's going to happen because our input to the rasterizer is going to be the same. For all three vertices in this triangle, if we give it the same normal, we're going to get very close to the same color back out, if not the same exact color back out. Certainly for a distant viewer, we're going to get effectively the same color back out. So that is the flat shading model. The Gerard innovation or the modification of it is to instead realize that, well, our vertex isn't just there in isolation, and it's generally, if we're in a mesh, if it's a real three-dimensional object, it's generally not corresponding to just one polygon. It's connected to multiple of those. So if we take a reasonable average of those individual normals, then for the Gerard shading implementation of the Phong lighting model, we can now calculate a reasonably different surface normal for each of the individual vertices in a given triangle, and that would give us different shades that we could then rasterize and interpolate across the individual triangle. That is the Gerard shading per vertex shading approach. They're both per vertex, but this one we would expect to get significantly different results per vertex for a given primitive because we're doing an averaging of the normals. So how we're calculating the normals becomes differently. And then oftentimes then finally when we're talking about the Phong shading model, and in the example that I was actually just bringing up in terms of the fragment shader that's happening here, what we instead do is a per fragment or per pixel shading, which would be instead of doing really anything in the vertex shader with regards to calculating a shade, instead all we are doing in the vertex shader is calculating a transform to normal. Model view matrix comes in that requires us to move our normal around. Again, then at this point, it doesn't matter so much if that input normal is very intelligently defined or if it's just the same for all the points in a given triangle, because either way, we're transforming it via our model view transformation, and then that is our output of the vertex shader, and output of our vertex shader then goes to our rasterizer, and then it's the actual surface normals that are getting interpolated or getting rasterized. So actually, that was one of the questions in the chat. Yes, that's exactly what this model is then doing. Our true Phong or our per fragment or per pixel shader is there's still work for the vertex shader to do. Transform my normals for me. We have just a transform normal per vertex. That is the output of the vertex shader. So before it gets to the fragment shader, it gets rasterized. We then do this interpolation to calculate what the quote unquote correct normal should be on a per fragment by fragment basis. right? They get rasterized like anything else, right? Our hardware, the hardware that you built, doesn't really know all that much, right? It knows that we have positional data in screen space, and that lets us figure out what the gradient is, but that gradient is per attribute for all the other attributes. We've been using it for color by and large, but there's nothing that prevents us, and you could implement this right now, and it should work for your MP3 level hardware. There's nothing preventing us from interpolating the actual normal values themselves. And then we can apply effectively the same approach, but doing it on a fragment by fragment basis. And it's not to say one is better than the other, right? There's trade-offs involved, right? Fragment shaders are more expensive than vertex shaders from a performance perspective, for the simple reason that by and large, you'll have many more fragments than you have vertices as an input to a given scene to be rendered. So if we could do all of our shading here with a flat model or a Gerard model, performance-wise, it should still be better. But in terms of a smoothness, I wouldn't necessarily say accuracy, because we're well beyond anything that's dealing with physically, accurately, mathematically accurate models of our lighting. But in terms of at least the resulting smoothness, your triangles are going to have nice gradients associated with them, and they're not going to look flat. They're not going to look like, yes, our three-dimensional object has contrast to it and has these gradients, but each of the triangles are all basically made of the same color. Now at least the triangles themselves, because we're interpolating the normals and then applying the Phong model on a fragment by fragment basis, each of our triangles will have these nice gradients associated with them. Yeah, that's exactly what I just mentioned there. So that's the Gerard shading, where no matter what, we can do so. But if we're not careful, our vertex shades are the same across each. Uh, if they're the same for all three input vertices, they'll be the same for each of our fragments. Instead, for sort of the per fragment or per pixel shading model, we actually just are calculating the vertex normals, and then the actual light calculations, and the math is still the same. The actual light calculations then happen on a fragment by fragment basis, and it's the actual the vertex normals themselves that are getting interpolated. But that does lead us to the um, next topic. When applying just lighting models, there's definitely limits of what can be done. Um, and you tend to see of just applying pure light models, lit toruses and teapots and spheres and things like that. It's a good starting point, but that lighting model, as relevant as it still is still very much insufficient for modeling real phenomenon. If I asked you to model um, how about just an orange, right? So we had Happy Fun Ball, which is probably still okay using this model. But if we actually wanted to model an orange using this lighting model, well, we certainly couldn't start with this. I mean, we could start with a sphere, but an orange is not an orange colored sphere, right? It's of roughly that shape, but it has a lot of more subtle detail associated with it. And Ryan, your point is correct, right? I mean, ultimately, everything is going to get broken down into triangles for this sort of traditional rendering pass that we are providing here. Um, so your question about points, well, points then fragments. Um, so there's let's use the right terminology here. Um, you'll have a certain number of input vertices, right? Those are three per triangle. And depending on the shape, we don't have to send three because we can use meshes and things like that. But still, let's just say three per triangle. And then the triangle itself will generate fragments. Right? The rasterizer will generate fragments from our triangle. And you can have very small triangles. You can have a triangle that's less than, I don't know. You can have a triangle that's small, so small that it's just one fragment. But generally, triangles are larger than that. And there's a certain number of fragments per triangle. But then ultimately, there are pixels in our final scene, and there's generally going to be many more fragments than there are pixels in a scene because of our MP4 stuff, right? I'm drawing this triangle, and then this triangle on top of it, and then this triangle on top of it, and I'm doing that, thousands of times for a sufficiently complex scene. Each of those are generating fragments. Those are just fragments that are not making it to the color buffer because of the render output hardware that you are right now in the process of implementing. So to be truly precise, there may not be many more pixels than there are vertices, although there can be. You can have one very large triangle, right? Um, but there's certainly many more fragments than there would be vertices in a given scene, because in any sufficiently complex scene, there's a lot of things we're rendering, but we have the pixels ultimately is always fixed by our resolution. I think that follows that. So yeah. So we could talk about bump maps. We'll get there. But even before we even talk about bump maps, the shapes themselves, there's a limit to what we can do with geometric modeling. I think. We could. I mean, given enough vertices and enough fidelity of a model, anything can be modeled, right? You can scan anything. In theory, you can 3D print anything. I mean, there are approaches that can allow you to or 3D scan anything to do that level of modeling, but there's a limit to it, right? In terms of the complexity of the model versus the fidelity of the resolution of the object that we would want to render. So it's not impossible, but there's limiting utility in just increasing the geometric complexity if we wanted to render something like an orange. And while the lighting model helps, the lighting model makes it so it's not just a circle when we're trying to view it in the scene. And the lighting model can help. We can model individual little imperfections and bumps in a given orange. Um, Ultimately, the real world is at a much higher resolution, right? And the fidelity of what we want to be able to view and see in a given scene would really be limited if we were trying to make everything a type of a triangle of a particular shade. So this is a very brief, kind of motivation for why we would potentially be interested in, applying texture to objects. Maybe this audience and you this point in the semester, how far we've gotten, you don't need me to motivate why we would have to do texture mapping. Um, but the idea is that by taking some uh, pre-calculated, pre-rendered perhaps image and applying it to the object, mapping it to a geometric object, you can get a lot more increase in detail without a corresponding increase in geometric complexity. This is straight from the Ed Angel textbook, this example here, but this is a shaded and lit model, a model with some amount of complexity to it. But if we were to try to make this into a really accurate orange, I think it'd be still quite difficult. And the only difference in these renders now, it's not the lighting model, which is, I think, fixed for these, but is which texture is being applied to that particular object that we have here. And you already brought up bump mapping, that's also a possibility. But the idea is we are calculating the final shade of each individual fragment now no longer just by what we get when we're rendering a triangle and rasterizing a triangle and shading a triangle via a Phong model or others, but also via some pre-calculated, and pre is a relative term here, but a priori calculation of what the corresponding location could be given a 1D, 2D, or 3D texture maps. Um, and whether these things are truly offline or online really depends. So there's nothing in this depiction of these additional three spheres here that tells us, is this something that is static or is it dynamic? The trade-off is really just one of performance. So this is an example of an environment map. We'll talk a little bit more about environment mapping. It's nothing that we can't potentially do, right? So the idea is that you're getting something of a correct mirror image of what if this was a really metallic sphere here of what it would see as reflecting off the rest of the scene without having to do necessarily a physically based render. And there's ways one can do it by initially rendering the scene, calculating what everything would be relative to the perspective of that as the camera in the scene, and then using that to calculate a texture, and consequently mapping that to the particular object here. There's limits of that, right? Because that's for one mirror-like object in the scene. Now, what happens if I have two and I have three? Then it becomes kind of an exponential pre-calculation that would be required. And likewise, it's expensive to do that. You're roughly calculating every scene twice just to get that small texture map for that particular object. Oftentimes, it's sufficient to say, well, in general, here's what the scene would look like. Calculate it once, store that in a file somewhere, and just load that as a texture map. But that would be an example of an environment map. it's whether it's truly an environment map, if it's done completely offline or not. I mean, that's a semantic argument, but the idea is you're getting a reflection for free by pre-calculating it. How much in advance is that pre-calculation is a semantic argument. There's other things you can do as well. We can also use to get something like a bumpier type of orange. We can do a bump map. We can have displacement of either vertices or the z dimension of our fragments. We can't do x and y, but of the z dimension of our fragments via a texture that tells us here's how much we would like to move this object based on a more realistic 3D model for what that object could be. All those things are possible with texture mapping. I think there's enough to cover for us and enough for you to implement to just say, we want to apply wrapping paper to our object. So given, and I think we would want to stick with just a 2D texture map in terms of how we think about things. Given a 2D texture, we want to wrap an object with that 2D texture to change, to either modulate or just completely replace what the shade of that object should be. It is a complementary approach to our lighting model, but it tends to allow us to have a lot more physical realism because the real world is very detailed. I take a photo that has incredible amount of detail. Instead of trying to model all the complexity of what I took in that photo, we can take some aspects of that photo and say, we're going to just do wrapping paper. We're going to map that to the particular object via this texture lookup mechanism. A couple questions I want to make sure I'm responding to everybody. So Mike, I kind of got to your question, but the answer is depends, right? Depends on how dynamic you want the lighting model to be. Because the trade-off is how much time at runtime is spent generating texture map versus just taking pre-generated texture maps and applying them to a particular object. In general, we are allowed to, at runtime, calculate texture maps or modify existing texture maps. How realistic we want the resulting texture to look like is just a performance and fidelity kind of trade-off that we're taking there, right? So in theory, you can do this in runtime with reasonably good accuracy. The trick is to render a scene as if this was the camera. This location is where the camera actually was. Use that to generate a texture map, and then in a separate pass, map that to that particular object. With one ball, it's not so bad. We can probably do it, right? But we generally aren't interested in just mapping a single ball, right? We have always it's a room full of marbles. Usually, we want to do our render of, and then they're partially transparent and partially reflective, and that becomes very expensive. It is still possible. Yeah, so it is in a sense ray. Well, you can do it via ray tracing, but the approach that people would refer to is just ray casting, which is what would be the view of light from this object's perspective. So that's how it would be done, and it is essentially ray casting. It is we have a camera, and what is the light that's entering that camera from all the objects contributing to that particular scene. So it could be done as someone is walking by it. Each frame that you're wanting to update the frame, you would have to render it effectively twice, which is what is the view from the mirror's perspective, and then what is the view from the actual camera's perspective, and combining those two together gives you your texture for that particular object there. I think, though, the big takeaways, yeah, there's a lot of very cool things one can do with it. The technique, the actual hardware for it, is exactly the same. And what we wind up seeing as we implement our texture fetch unit for MP4, fingers still crossed that we can get something working for MP4 with our texture fetch unit. I've resorted to fingers crossed as our strategy for getting this to work. Is a very small amount of programmability. The actual function or instruction you want to think about it is relatively straightforward. There's 1D, 2D, and 3D variants of it, and a couple other parameters. If we stick with the 2D case, it's really just a single instruction. But what it has is an absolute ton of configurability for it. It is not so different than old school kind of fixed function texture fetch units. The only difference now is the different places we can apply it in our graphics rendering pipeline. Let's talk about textures and certainly start with the basics, right? So we can have a very complicated model, and shaded it can look reasonably realistic, but only when a texture is applied to it do you start to get that real kind of 3D realism of it. So there are limits. There's a lot of things we can do with just geometric complexity, but there's limits to that as well. And you can see, while this is a very realistic looking in the sense of a lot of level of detail, there's a very detailed view. This is a much more realistic, to some reasonable extent, view of the same model here, because we've just taken our shaded model, which captures all that geometric complexity, and then we've been able to add an extra level of detail that would be very difficult to also just capture via geometric complexity. There are no fundamental limits of our geometric complexity. It's really just performance considerations of how many triangles do we want to make every individual model to render something realistically? How many material and light interactions do we want to have to be able to model for it? Versus a hippo's a hippo. Here's our hippo skin. We apply it to the individual model that we have there, and that is the basic approach. And I think if you get this part, you're in pretty good shape for today's topic. With as we introduce texture mapping, we are just for each triangle, as we're doing our rasterization of the triangle, we're just going to establish a corresponding region in the image to be mapped. That is all that's happening here. Think of it like wrapping paper, but it's being applied on a triangle by triangle basis. So depending on where we are doing the texture mapping, what generally happens is at the vertex shading side, we establish those coordinates. Either they're just an input or they're calculated as part of our vertex shader and then they're passed through the vertex shader. That gives us the coordinate locations for those three particular points. And we generally don't do it in image space. It's done in this texture space, which is between coordinates of 0 and 1 by and large. But you can think of them as corresponding to pixel locations in our image here. The vertex shader for the three vertices calculate what those, or we calculate or are given what those three coordinates would be. And consequently, when we're rasterizing this triangle, we're also then rasterizing or interpolating those texture coordinates. So when we made the decision this semester to have basically four things that we pass down our pipeline, it's still a pretty decent decision from the perspective of getting realistic looking images. We have to pass positional data through. It's nice to have color data through, even if later you choose not to use it. We have space to then pass surface normals through, and we have space to pass a couple different set of texture coordinates through in our system. And that's what we connect together, and that's what we would be interpolating here, right? So if this location, I'm sure you can't read it, is 251, 170. Well, our rasterizer is going to take care of that for us. It's very good at doing that, right? It's very good at rasterizing given um, a delta x and a delta y. It'll tell us for each of those individual fragments we're generating what the XY location should be, as well as where the individual texture coordinates would be for that new XY location that we are generating. Everything that's inside the triangle would then have a corresponding texture coordinate on a fragment by fragment basis. Yeah, it's hard to say, for that particular object, how well it would look in practice. There's a general challenge in um, high level of detail in textures as mapped to geometric objects. But as we have more and more triangles, we can have more and more precision with how we're doing that texture mapping, right? So this example isn't quite correct in that sense, right? This is a pretty big chunk of the texture we're showing here, just to illustrate it, but a very small chunk of the actual object. So in practice, um, there would presumably be a reasonably similarly sized, part of the texture we would attempt to map. But you do tend to see that with all sorts of texture mapping as applied in practice. You still have to have a certain level of geometric detail to have a certain level of fidelity in the texture mapped object that we have back out. Let's leave it with just this final example of what this looks like in practice. So if we have a quad, we can think of it as our two triangles here. We would then also have a texture, an actual image array associated with it. Think of it as a two-dimensional array of memory or a file that we're eventually loading. So many of the examples we do are checkerboards, because then you don't have to worry about reading a file in your code. You're just doing black and white, checkerboard arrays that you're pre-calculating. But fine, assuming we've loaded awesome.jpg here, we would have, as we are specifying the positional attributes for each of our incoming vertices. For our first triangle, we'll say it's v1, v2, v0. As we specify that triangle's positional attributes, and we do the model view and all that kind of stuff, right? We're specifying dot x, dot y, and dot z for v1, v2, and v0. To do texture mapping, we would also be specifying texture coordinates at the same time we're specifying our positional information. And they can be similar looking, but their purposes are different. You can think of these texture coordinates, and UV is a common. You see S and T. You see TX, T sub X, T sub Y. Depends on whose resource you read. UV is what OpenGL uses, so we're okay with that. I think using that by and large, at least the examples we see should use U and V as our texture coordinates. You can think of these texture coordinates as a clamped value, or at least a normalized value, indicating our X and Y dimension of the actual two-dimensional image map we're wanting to reference. So when we specify that for V1, which is our XYZ position for this vertex, we're also specifying two more dimensions, basically, a U of 1 and a V of 0. We are specifying that for this vertex, it should have, oh, you can't see my mouse, it should have this coordinate. Likewise, for V2, it's 1, 1, it should have this coordinate. For V0, it should have this coordinate. And for V3, which if it's a quad, but otherwise it's the lower left-hand side of that second triangle, if this was a triangle strip, it would be this coordinate. And at least conceptually, there's a little bit of care we have to take as we're implementing this. What happens? We specify those as attributes. That vertex passes the U and V value into our rasterizer. We get a triangle. Well, if this one is 1, 0, and this one is 1, 1, then for whatever this fragment here corresponds to, it'd be roughly 1, 0.5, right? And for the rest of them as well. We would then be rasterizing, and generally that works pretty well for two triangles comprising a flat quad, that, with no perspective at least, that when we do so, we get back out a position, an index into this that is done in that kind of normalized, clamped kind of format here. You can think of them as pixel coordinates as well, but that's what that sampler function and what that texture look is ultimately going to be doing. That now in our fragment processing, given a UV that would be, for example, for this one, 1, 0.5, look up into the image what actual byte or bytes that would correspond to, and then that becomes at least some component of our final shade as the output of our fragment shader. So you would get roughly this. Given awesome.jpg, there's a little bit of distortion. I look slightly more squat and fat than I am in practice as we apply this. Separately, if we now have a second texture, other.jpg, we can apply for these points up here in our cube a set of different UV values. And we tend to think of it as being between 0 and 1, but as we'll see, and I don't know how much of this we'll cover in practice, there's a wide range of configurations for my texture as a file, my texture as a block of data, my texture as being mapped to my texture unit. It's pretty large in terms of the configuration space, but one thing we can specify is a clamping or repeating mode of the texture, such that if we specify, you may be able to see where this is going, you may not, for V7, V8, V1, V0, we're specifying this is not 1, 0 and 1, 1, we're specifying it as 4, 3. Depending on the mode in which we are doing texture mapping, it'll still get interpolated. If this was 4, 0 and this is 0, 0, then 1, 0 would be about right here, right? 2, 0, 3, 0, 4, 0 in terms of our interpolated fragment texture coordinates. What'll happen, it depends on how we configure our texture units to do that lookup, is that instead of having one picture of other.jpg, you would get some sort of multiple copies, in this case 4 copies in the X dimension and 3 copies in the Y dimension, or the U and the V dimension for that particular texture. Even for that simple example, which took way more time in PowerPoint than I would like to admit, there's a lot of care we're going to have to take, because even in this simple example, for this flat face, there's no necessarily issue with it. But for this one, we now have an issue with perspective. And that's where I'd like to leave things for today. That applying this is not as straightforward as just a memory lookup. We have to do some more processing before we get to the point of doing our memory lookup. Otherwise, we're going to get a result that's not exactly what we would expect back out. For the same reason, we have to be aware of perspective when doing our vertex shading and our rasterization. We have to do the same thing with regards to our texture coordinates as well. Let's leave things here for today. I'd really love to see teams sprint on both, getting the basics of MP4 working, getting shading and the vertex and fragment shading to do something, and then playing around with what's possible with regards to your shaders to be able to show off that you understand the flow, you have cores that can actually do some reasonable processing and aren't just being used as a very ineffective, kind of pass through copying of data. I think that'd be nice to see. I know not all teams will get there, but then the hope is we can then transition and you can really get started in earnest on your projects. And I know there's an ambiguity with regards to MP4 in terms of, well, which of these render modes do I have to support for depth testing? Which of these alpha modes do I have to support? Certainly, which of these texture modes do I have to support? We haven't covered it all yet. The answer is pick a reasonable subset. Pick something that you can get to work in a reasonable amount of time. Once you have that working and you have more bandwidth, you can get more things working. Basic depth testing and alpha blending is something that is just a few more states in your render output state machine, and I'd hope that at least all teams for Thursday would be able to show that off. But let's use that time in lab on Wednesday to do some final debugging to figure out some of the challenges of getting the fragment shader integrated. And I'm really looking forward on Thursday to see what you come up with, and hopefully a couple fun one-off demos that you can show the rest of the class on Thursday. So let's leave things here for today. Looking forward to seeing you tomorrow and on Thursday, and enjoy.